What if everything you thought you knew about empty space was wrong? Picture this everywhere around you, right now. Even in the so-called void between stars, there's an invisible storm raging. A storm so small, so fleeting, that it defies everything our senses tell us about reality. This isn't science fiction. This is quantum foam, the hidden, chaotic underbelly of the universe where particles wink in and out of existence faster than a blink, where the very fabric of space and time is constantly twisting, tearing, and stitching itself back together. And here's the wildest part. This isn't just some abstract idea. Quantum foam might hold the keys to understanding the biggest puzzles in physics, from the strange pull of dark energy to the fiery hearts of black holes. Think about the last time you stared up at the night sky, marveling at the vast, silent emptiness between the stars. It turns out that emptiness is anything but empty. It's a seething ocean of potential, a place where the rules of physics as we know them break down and rewrite themselves in ways that still baffle even the brightest minds. Why should you care? Because this isn't just about distant galaxies or theoretical equations. This is about the universe's blueprint, the hidden code that shapes everything from the tiniest particle to the grandest cosmic structures. And the more we uncover about quantum foam, the closer we get to answering questions that have haunted humanity for centuries. Where did everything come from? What lies beyond the edge of a black hole, and what truly is the nature of reality itself? So buckle up. Over the next few minutes, we're going to venture into this strange, shimmering world where nothing is as it seems. We'll explore how scientists first stumbled upon the idea of quantum foam, how it challenges our most fundamental assumptions, and why some researchers believe it could be the missing piece in our quest to unite the laws of the very large and the very small. By the time we're done, you won't just see empty space differently, you'll feel it, because the universe is far weirder, far more alive than we ever imagined. And this is just the beginning. To grasp quantum foam, we need to shrink down way down, to scales so tiny they make atoms look like planets. Here, in this microscopic realm, space-time isn't smooth and predictable like a calm pond. Instead, it's more like the surface of a boiling pot, bubbling with frenetic energy. This isn't just poetic imagery. It's the direct result of one of quantum mechanics' most mind-bending rules, the uncertainty principle. At its core, this principle tells us that even in a vacuum, energy can't sit perfectly still. There's always a little wiggle room, tiny fluctuations that allow particles to momentarily borrow energy from the universe, exist for a heartbeat, and then vanish back into the void. John Wheeler, the visionary physicist who coined the term quantum foam, likened it to the froth on an ocean wave, a churning, dynamic landscape where the very geometry of space-time becomes fuzzy. Imagine trying to measure the surface of a bubble with a ruler. The closer you look, the more the edges shimmer and twist. That's space-time at the quantum level, a realm where distances and durations blur, where here and now lose their usual meanings. These wild fluctuations aren't just theoretical quirks, they have real, observable effects. For instance, the Casimir Effect, where two metal plates placed incredibly close together in a vacuum inexplicably attract each other, is direct evidence of quantum foam's restless energy. The plates squeeze out some of those virtual particles, leaving fewer to push outward, and the result is a measurable force. But here's where it gets even stranger. Quantum foam doesn't just tweak the rules, it rewrites them. In this chaotic subatomic arena, Einstein's smooth, warped spacetime collides head-on with quantum unpredictability. Gravity, which normally sculpts the cosmos on grand scales, becomes just another player in this turbulent microscopic dance. Some theories suggest that at these infinitesimal distances, space-time itself might be pixelated, like a cosmic digital image where the pixels are grains of reality far smaller than anything we've ever detected. This isn't idle speculation. If we could probe these scales something far beyond today's technology, we might finally uncover the missing link between quantum mechanics and gravity, the holy grail of modern physics. So what does this mean for our understanding of the universe? It means that emptiness is an illusion. The void isn't passive or barren. It's a hive of activity, a place where the universe constantly reinvents itself. Every cubic inch of so-called nothingness is, in truth, a storm of creation and destruction, a ceaseless ballet of particles and forces that shape everything from the stability of atoms to the fate of galaxies. And while quantum foam might seem like an abstract curiosity, it's anything but. It's the hidden engine of reality, the unseen hand that molds the cosmos. And the more we learn about it, the more we realize how much we've yet to discover. The uncertainty principle isn't just some abstract rule. It's the universe's way of keeping us humble. Imagine trying to take a photo of a hummingbird in mid-flight. The faster its wings move, the harder it is to pinpoint their exact position. Now shrink that scenario down to the quantum scale, where particles move at unimaginable speeds, and you begin to see why Heisenberg's principle shakes our understanding of reality. At this level, the very act of measurement disturbs the system, creating a fundamental limit to what we can know. But here's the twist. This limitation isn't a flaw in our tools or methods. It's woven into the fabric of existence itself. These quantum fluctuations are like cosmic pop-up adds particles and their antimatter counterparts appearing out of nowhere, borrowing energy from the vacuum and vanishing before they can be caught red-handed. An electron and a positron might blink into existence for less than a trillionth of a second, only to collide and disappear in a tiny burst of energy. This isn't hypothetical. We've observed the aftermath of these ghostly performances in experiments like the Casimir Effect, where the relentless dance of virtual particles creates measurable forces between objects. Picture two microscopic plates hovering in a vacuum. Normally, you'd expect nothing to happen in empty space, but the quantum foam has other plans. The plates act like walls, limiting the kinds of fluctuations that can occur between them. Outside, the vacuum buzzes with unlimited possibilities, pushing inward with more pressure than the restricted space inside. The result, the plates are nudged together by the sheer weight of nothingness. What's truly staggering is how these fleeting fluctuations scale up. The same quantum jitters that tug those plates together might also hold clues to the universe's accelerating expansion. Some theories suggest that dark energy, the mysterious force driving galaxies apart, could be tied to the vacuum's intrinsic energy, a sort of background static left over from these endless particle collisions. Even black holes, those cosmic vacuum cleaners, might owe their terrifying power to quantum foam. Near the event horizon, virtual particles can be ripped apart before they annihilate, with one falling into the abyss while the other escapes as radiation. This process, known as Hawking radiation, suggests that even the darkest corners of space are shaped by quantum uncertainty. So when we talk about quantum foam, we're not just describing a quirky side effect of physics. We're staring into the engine room of reality, where the universe's most basic operations play out in a frenzy of creation and destruction. Every second, countless particles surge into existence and vanish, their brief lives leaving faint echoes in the fabric of space. And while we may never see them directly, their fingerprints are everywhere, from the forces that bind atoms to the vast, invisible tides shaping the cosmos. The void isn't empty, it's alive. Einstein's vision of the universe was elegant, precise, a cosmic ballet where gravity curved the stage of spacetime in predictable, beautiful arcs. To him, the idea that reality might be built on randomness was unthinkable. Yet quantum foam throws that certainty into chaos. Picture two artists painting the same canvas. One uses broad, sweeping strokes to create a seamless landscape, while the other stipples the surface with frenetic dots. That's the tension between general relativity and quantum mechanics. One sees spacetime as a smooth fabric, the other reveals it as a seething swarm of ephemeral particles. This isn't just academic debate. The conflict between these theories shapes how we understand everything from the birth of the universe to the fate of black holes. Take gravity, for example. Einstein described it as the curvature of spacetime planets and stars bending the cosmic sheet like weights on a trampoline. But zoom into the quantum scale, and that smooth sheet frays into a turbulent foam. Here, gravity doesn't behave like a gentle slope. It crackles with unpredictability, appearing and vanishing in fits and starts. The math that works flawlessly for galaxies falls apart in this subatomic storm. That's why physicists are so obsessed with finding a theory of quantum gravity, a framework that could reconcile these two visions. Some propose that spacetime itself might be woven from tiny, indivisible loops or strings, a fabric stitched together at scales a billion trillion times smaller than an atom. Others suggest that quantum foam isn't just noise but a hidden language, a code that could reveal how gravity emerges from the chaos. Imagine trying to hear a symphony in a thunderstorm. Right now, we're only catching fragments of the melody, but the right theory might tune our ears to the full composition. What's at stake goes far beyond equations. If we can crack this puzzle, we might finally answer why the universe exists at all. The Big Bang, black holes, even the arrow of time. All these mysteries hinge on understanding how gravity dances with quantum mechanics. Einstein's resistance to randomness wasn't just stubbornness. It was intuition that the universe must have deeper order. Quantum foam, for all its chaos, might be the very thing that leads us there. The dice may roll, but perhaps they're loaded in ways we're only beginning to glimpse. Virtual particles are the universe's ultimate tricksters, fleeting, elusive, and utterly unpredictable. They're not like the electrons or protons we're familiar with. Instead, they're more like shadows cast by the quantum world, flickering in and out of existence so fast that they defy direct observation. Think of them as cosmic loan sharks, borrowing energy from the vacuum of space just long enough to make their mark before vanishing without a trace. And here's the kicker: this isn't some exotic phenomenon happening light years away. It's unfolding right now, in the space between your fingertips and the screen you're staring at. Take the Lamb shift, for example. Back in the 1940s, physicists Willis Lamb and Robert Rutherford noticed something bizarre about hydrogen atoms. The energy levels of their electrons didn't quite match the predictions of quantum theory. The discrepancy was tiny, almost negligible, but it was real. After years of head-scratching, the answer emerged: virtual particles. These ghostly entities were popping up around the electron, distorting the electric field ever so slightly and tweaking its energy. It was as if the electron was swimming through an invisible sea of foam, constantly jostled by particles that shouldn't exist. This wasn't just a mathematical quirk. It was hard evidence that the vacuum was alive with activity. But how can something that doesn't stick around long enough to be measured still affect the world? Imagine throwing a pebble into a pond. The ripples spread out, interacting with everything they touch, even though the pebble itself has sunk to the bottom. Virtual particles work the same way. They leave behind fingerprints, subtle nudges and tweaks that ripple through the fabric of reality. In particle accelerators, for instance, these fleeting interactions can influence the outcome of collisions, skewing results in ways that only make sense if you account for the vacuum's hidden turmoil. Even light itself isn't immune. When photons travel through empty space, they can briefly split into virtual particle pairs, subtly altering their path or energy. It's as if the universe is constantly whispering secrets just below the threshold of perception. The implications are staggering. If virtual particles can shift energy levels and bend light, what else might they be capable of? Some theories suggest they could play a role in the universe's expansion, their collective energy contributing to the mysterious force we call dark energy. Others speculate that they might hold clues to the nature of time itself. After all, if particles can borrow energy from the future to exist in the present, even for an instant, what does that say about causality? The more we learn about these phantom particles, the clearer it becomes. The quantum foam isn't just a curiosity. It's the scaffolding of reality, a hidden layer of chaos that underpins everything we know. And while we may never catch these ghosts in the act, their echoes are everywhere, reshaping our understanding of the universe one fleeting interaction at a time. The Casimir Effect isn't just a quirky lab result, it's a cosmic wake-up call. Picture two thin metal plates, perfectly smooth, placed so close together in a vacuum that there's barely room for a single atom between them. Logically, nothing should happen. No wind, no charge, no obvious force at play. Yet against all intuition, the plates inch toward each other, as if pulled by invisible strings. This isn't magic, it's quantum foam flexing its muscles. Back in 1948, Hendrik Casimir cracked the code. He realized that even in a vacuum, the space between those plates isn't truly empty. It's buzzing with virtual particles, ghostly duos of matter and antimatter that flicker into existence for fractions of a second. But here's the twist. The plates act like bouncers at a club, only letting certain wavelengths of these particles party in the gap. Outside, the vacuum is a wild rave, packed with particles of all sizes. Inside, only the tiniest fluctuations fit. That imbalance creates a pressure differential, with more virtual particles pushing inward than outward, nudging the plates together. The result, a force so subtle it's measured in billionths of a Newton, but so profound it rewrites our understanding of nothingness. What makes this phenomenon so groundbreaking isn't just the math, it's the tangible proof. In the late 1990s, physicists at the University of Washington finally measured the Casimir force with exquisite precision, using gold-coated plates and lasers to track their movement. The numbers matched Casimir's predictions almost perfectly. Suddenly, quantum foam wasn't just a theory scribbled on chalkboards, it was a measurable player in the physical world. Think of it like hearing whispers in a silent room. You might not see the speakers, but their presence is undeniable. But the real kicker, this effect scales. While lab experiments use microscopic plates, the same principles apply across the cosmos. Some scientists speculate that quantum foam's pressure might influence the behavior of nanoscale machinery, or even play a role in the stability of atomic nuclei. Others wonder if it could help explain why the universe's expansion is accelerating, that perhaps the vacuum's latent energy, hinted at by the Casimir effect, is the engine behind dark energy. It's a staggering thought. The same force that tugs those tiny plates together might also be driving galaxies apart. The Casimir effect does more than confirm quantum foam's existence. It reveals a universe where emptiness is an illusion. Every cubic centimeter of space, whether between stars or between your fingertips, is a seething hive of potential. And while we can't see these fleeting particles directly, their fingerprints are everywhere, bending light, tweaking energy levels, and now, thanks to a Dutch physicist's brilliant hunch, pushing metal plates in a vacuum. The void isn't passive, it's a participant shaping reality in ways we're only beginning to grasp. Black holes aren't just cosmic vacuum cleaners, they're quantum foam's ultimate stress test. Picture the edge of a black hole's event horizon, where gravity is so intense that not even light can escape. Here, in this violent twilight zone, the fabric of spacetime isn't just warped, it's shredded. Quantum foam, usually a background hum of particles flickering in and out of existence, erupts into chaos. Pairs of virtual particles, normally born and annihilated in perfect sync, get ripped apart by the black hole's gravitational fury. One particle gets swallowed by the abyss, while its partner escapes into space, stealing a tiny bit of the black hole's energy in the process. This isn't theoretical guesswork. It's Hawking radiation, the phenomenon that proves black holes aren't eternal. They leak, they fade, and it's all thanks to quantum foam's relentless churn. Stephen Hawking's revelation in the 1970s turned astrophysics on its head. Before his work, black holes were thought to be one-way streets, cosmic traps where matter and energy entered but never left. But Hawking showed that quantum foam changes the rules. Those escaping particles carry away energy, causing the black hole to slowly evaporate over unimaginable timescales. A stellar mass black hole might take longer than the current age of the universe to vanish, but the principle remains. Quantum mechanics gives black holes an expiration date. It's as if the universe has a recycling program where even the most destructive objects eventually return their energy to the cosmic pool. The implications go far beyond black holes. This process is one of the few known bridges between quantum mechanics and gravity, two theories that otherwise refuse to play nice. In the maelstrom near the event horizon, gravity's smooth curvature crashes headlong into quantum foam's frenetic randomness. Some physicists believe that studying this collision could reveal the missing pieces of quantum gravity, the grand unified theory that has eluded science for decades. Imagine trying to understand a storm by watching how it bends trees. Hawking radiation is like those bending trees, a visible clue to invisible forces. If we can decode how quantum foam behaves under such extreme conditions, we might finally understand how gravity operates at the smallest scales. But here's the catch: Hawking radiation is incredibly faint, drowned out by the cosmic microwave background and other noise. Detecting it directly is beyond our current technology, yet clever workarounds exist. In 2014, lab experiments using flowing water and laser pulses simulated black hole event horizons, observing analogs of Hawking radiation in controlled settings. These aren't perfect replicas, but they hint at universal principles, suggesting that the connection between quantum foam and black holes isn't just a cosmic fluke. It's a fundamental feature of reality. What's truly mind-bending is the possibility that black holes aren't unique. If quantum foam can unravel them over time, could it also shape other cosmic phenomena? Wormholes, singularities, even the Big Bang itself might owe their behavior to this subatomic turbulence. The more we learn, the clearer it becomes. Quantum foam isn't just a backdrop. It's an active sculptor of the universe, carving out realities we're only beginning to imagine. And black holes, with their fiery dance of creation and destruction, are the perfect lens to bring this hidden world into focus. Dark energy is one of the greatest mysteries in modern cosmology, a force so enigmatic that it makes up nearly 70% of the universe's total energy, yet we can't see it, touch it, or even fully explain it. But what if the answer lies in the quantum foam? That same turbulent sea of virtual particles we've been exploring might hold the key to why the cosmos isn't just expanding, but accelerating apart at breakneck speeds. Here's the puzzle. According to quantum field theory, the vacuum of space should be bursting with energy. Every flickering virtual particle pair contributes to what's called vacuum energy, a background hum that, if you add it all up, should be astronomically powerful. We're talking energy densities so vast they'd rip spacetime apart. Yet when astronomers measure dark energy's actual effect, it's vanishingly weak, a whisper compared to the theoretical scream. This mismatch, known as the cosmological constant problem, has haunted physicists for decades. It's like calculating the roar of a jet engine but hearing only the rustle of leaves. So where does all that missing energy go? Some theorists argue that unknown symmetries or cancellation mechanisms in quantum foam might be at work. Imagine two waves crashing into each other, one cresting while the other troughs, cancelling out to leave calm water. On a cosmic scale, perhaps the chaotic dance of virtual particles follows similar rules, with opposing fluctuations neutralizing most of the vacuum's inherent energy. What remains could be the faint residue we call dark energy, just enough to gently nudge galaxies apart. Others propose even wilder ideas. If space-time is fundamentally granular at the quantum level, like a digital image made of pixels, those tiny grains might impose a natural cutoff, preventing energy from piling up beyond a certain scale. Think of it like a sieve. Only the smallest fluctuations slip through, while the larger ones get filtered out. This could explain why dark energy is so feeble compared to predictions. The universe, in essence, has built-in limits to how much chaos it allows, but the most tantalizing possibility, dark energy, isn't static. Quantum foam's fluctuations might mean its strength changes over time, slowly diluting or intensifying as the universe evolves. If true, this could reshape our cosmic destiny. A weakening dark energy might one day halt the expansion, leading to a big crunch. A strengthening one could tear atoms apart in a big rip. Right now, we're left reading the tea leaves of supernova and galaxy clusters, searching for clues in the light of distant stars. Whatever the answer, one thing is clear: quantum foam isn't just background noise. It's a dynamic, living layer of reality that might hold the secrets to the universe's past, present, and ultimate fate. And as we peel back its layers, we're not just solving equations, we're decoding the story of everything. String theory turns the quantum foam from a chaotic storm into a cosmic symphony. Instead of particles randomly popping in and out of existence, imagine space-time composed of unimaginably tiny strings, vibrating filaments of energy so small that if an atom were the size of a solar system, a string would barely be a tree on one of its planets. These strings don't just buzz randomly, they dance to precise harmonics, their oscillations determining whether they manifest as electrons, quarks, or even the carriers of gravity itself. In this framework, what we call quantum foam might actually be the interference patterns of these strings, their overlapping vibrations creating the illusion of frothy spacetime at the smallest scales. The real magic happens when string theory introduces extra dimensions. We're used to thinking in 3 dimensions of space and 1 of time, but strings vibrate in 10 or 11 dimensions, most of them curled up so tightly that we'll never perceive them directly. Picture a garden hose stretched across a field. From far away, it looks one-dimensional, but up close, you see its circular surface. Those hidden dimensions could be the key to smoothing out quantum foam's roughness. Just as a tangled rope appears smooth when viewed from a distance, the apparent chaos of spacetime at the Planck scale might resolve into elegant geometry when seen through the lens of higher dimensions. This isn't just mathematical hand-waving. String theory's approach could solve one of quantum foam's biggest headaches: infinities. Traditional quantum field theory predicts that vacuum fluctuations should generate infinite energy densities, an absurd result that begs for a deeper explanation. But strings have a built-in cutoff length. Their tiny size prevents them from probing distances shorter than themselves, effectively placing a floor beneath the quantum froth. It's like trying to measure the ripples in a pond with a giant paddle. You simply can't detect the finest details. Suddenly, those runaway infinities vanish, replaced by finite, calculable values. Yet the most tantalizing possibility lies in brains short for membranes, theoretical objects where strings can anchor themselves. Some models suggest our entire universe might be a three-dimensional brain floating in a higher dimensional bulk. In this scenario, quantum foam's turbulence could be the holographic projection of strings interacting on the brain's surface, like ripples on a pond reflecting the motion of unseen fish below. This holographic principle implies that spacetime's apparent roughness is just a shadow play, a cosmic illusion hiding a deeper, more ordered reality. The question remains, can string theory bridge the gap between quantum foam's frenetic microcosm and relativity's serene spacetime? Early signs are promising. Certain string theory solutions naturally reproduce Einstein's equations at large scales while accounting for quantum jitters at small ones. Others suggest that the foam's structure might encode hidden symmetries, mathematical patterns that could unlock gravity's quantum secrets. But until we find experimental evidence, perhaps in subtle gravitational wave signatures or particle collider anomalies, string theory's vision of quantum foam remains a breathtaking hypothesis. What's clear is this: if strings are real, then emptiness isn't just frothy. It's musical, multidimensional, and far more elegant than we ever dreamed. Loop quantum gravity dares to ask a radical question: what if spacetime isn't smooth, not even foamy, but stitched together like fabric? Picture the universe as an intricate tapestry, woven from countless tiny loops so small that 1 billion of them could fit across a single atom. These aren't just abstract threads, they're the fundamental building blocks of reality, tying space and time into a dynamic, interconnected network. Unlike the chaotic froth of traditional quantum foam, loop quantum gravity suggests a cosmos with structure, a pixelated landscape where each pixel is a loop carrying a tiny bit of spacetime's geometry. This idea didn't emerge from nowhere. It's a direct response to one of physics' most glaring headaches: the clash between Einstein's general relativity and quantum mechanics. While string theory adds extra dimensions to smooth out the chaos, loop quantum gravity takes the opposite approach. It breaks spacetime down into its simplest possible components, like zooming in on a photograph until you see the individual pixels. The result, a universe where gravity isn't a continuous force but arises from the way these loops intertwine and interact. Imagine a mesh screen. Each intersection point represents a quantum of space, and the threads between them define how regions connect. Stretch or bend the screen, and you've got gravity in action. One of the theory's most stunning revelations is how it handles black holes. In traditional physics, anything crossing a black hole's event horizon gets crushed into an infinitely dense singularity, a mathematical absurdity. Loop quantum gravity offers an escape hatch. Here, the loop's finite size prevents infinite collapse, like a safety net woven into spacetime itself. Instead of a singularity, matter might rebound in a quantum bounce, potentially birthing new universes. This isn't just poetic speculation. Calculations show these loops could encode information about what falls into a black hole, preserving it in the fabric of spacetime itself. That's a big deal because it might solve Hawking's infamous information paradox, the puzzle of whether data swallowed by black holes truly vanishes. But how do we test something so abstract? The answer lies in the fabric of the cosmos. If spacetime is pixelated, then very high-energy light particles like gamma rays from distant supernova might stumble over these tiny loops as they travel across the universe. Just as a digital image gets blocky when you zoom in too far, light's wavelength could reveal spacetime's granularity. Experiments like the Fermi Gamma Ray Space Telescope are already hunting for these subtle distortions, though definitive proof remains elusive. Another clue might come from the early universe. Loop quantum gravity predicts that the Big Bang wasn't a singular explosion, but a rebound from a previous cosmic collapse. This Big Bounce scenario leaves fingerprints in the cosmic microwave background, echoes we might one day detect. What's mesmerizing about this framework isn't just its elegance, it's how it redefines emptiness. The void isn't a seething foam or a blank slate. It's a living lattice, a cosmic knitting project where every stitch matters. And while we can't yet see these loops directly, their theoretical ripple effects are everywhere, from the fate of black holes to the universe's first moments. Loop quantum gravity doesn't just challenge our picture of reality. It invites us to see the universe as a vast, dynamic web, one where every knot, every connection holds the secret to how everything fits together. The Big Bang wasn't just an explosion, it might have been a cosmic hiccup. Imagine quantum foam as an endless ocean, with waves of energy rising and falling in a chaotic dance. Most of these fluctuations vanish instantly, collapsing back into the void. But every so often, one grows just enough to escape its own annihilation, inflating faster than it can decay. That fleeting bubble could have been our universe's first breath, a random quantum burp that, against all odds, became everything. This idea, known as vacuum fluctuation cosmology, turns the traditional Big Bang narrative on its head. Instead of a singular, inexplicable beginning, our universe might be part of an eternal cycle, a single note in a symphony of cosmic births and deaths. Think of it like a pot of boiling water. Most bubbles pop the moment they form, but occasionally one grows large enough to break the surface. In this analogy, the boiling water is the quantum foam, and our universe is that rare, surviving bubble. The staggering implication: we might be living in one of countless universes, each with its own unique physics, forged in the foam's relentless churn. What's wild is how close this connects to observable science. The afterglow of the Big Bang, the cosmic microwave background, bears faint imprints of quantum fluctuations stretched across the sky. Those tiny ripples in spacetime's fabric, magnified by inflation, became the seeds for galaxies and cosmic webs. But here's the twist: if those fluctuations trace back to quantum foam, then the very structure of our universe, the distribution of matter, the strength of gravity, even the arrow of time, could be the result of a quantum roll of the dice. This isn't just philosophy. Some models suggest that the foam's turbulence might explain why our cosmos has the precise constants it does. If gravity were slightly stronger, stars would burn out too fast. If electromagnetism were weaker, atoms wouldn't hold together. Quantum foam could be the reason our universe is hospitable at all. Yet the most mind-bending possibility is the multiverse. If quantum foam continuously spawns universes, each with random physical laws, ours might simply be the lucky one where conditions allowed life to emerge. The others, they could be stillborn, collapsing instantly, or expanding into barren voids. This isn't science fiction. Theories like eternal inflation paint a picture where spacetime is a frothing sea of universes, each bubble forever out of reach of the others. We'll never see them, but their existence would mean that quantum foam isn't just part of reality. It's the ultimate architect, endlessly drafting new cosmic blueprints. The quest to understand this primordial foam isn't just about origins, it's about destiny. If universes can emerge from quantum fluctuations, could ours one day spawn new ones? Could black holes, those shredders of spacetime, be birthing new cosmos in their cores? The equations hint at eerie possibilities, where the boundaries between physics and metaphysics blur. Every time we peer deeper into the quantum foam, we're not just studying particles, we're reading the universe's autobiography, written in a language we're only beginning to decipher. And the story it tells, that nothing, not even the birth of everything, is ever truly random. The holographic principle doesn't just challenge our understanding of reality, it shatters it. Picture a movie projected onto a screen. Every explosion, every whispered conversation, every sweeping landscape appears three-dimensional, rich with depth and movement. But peel back the curtain and you'll find it all encoded on a flat strip of film. Now imagine that same illusion applied to the universe itself. What if the stars, planets, and even your own hands are nothing more than projections, holograms etched onto some distant two-dimensional surface? This isn't science fiction. It's a serious theory with roots in black hole physics and quantum foam's chaotic behavior. The idea first gained traction in the 1990s when physicists Gerard T. Hooft and Leonard Susskind made a startling observation. Black holes, they realized, obey a strange rule. The maximum amount of information a region of space can hold isn't determined by its volume, as you'd expect, but by its surface area. It's as if the interior of a black hole is nothing more than a shadow play, with all its secrets painted onto the event horizon. From there, the leap to the holographic principle was inevitable. If a black hole's contents can be encoded on its boundary, why not the entire universe? Quantum foam, with its seething network of virtual particles, might be the mechanism, a pixelated canvas where reality is rendered in bits far smaller than atoms. But how could this possibly work? Think of a computer game. The world you explore seems vast and detailed, but under the hood, it's all just code, mathematical rules generating the illusion of depth. Similarly, the holographic principle suggests that spacetime's three-dimensional richness emerges from quantum foam's underlying data, those fleeting particles and energy fluctuations. They might be pixels in a cosmic display, their interactions computing the universe in real time. Even stranger, this could explain why quantum foam appears chaotic. If reality is a projection, then the static we observe at tiny scales might be the glitches and artifacts of the encoding process, like digital noise in a compressed image. Evidence for this radical idea is still indirect but tantalizing. Certain models of quantum gravity, like string theories, add S/CFT correspondence, mathematically demonstrate how a higher dimensional space can be perfectly described by physics operating on its lower dimensional boundary. It's as if the universe has a built-in redundancy, a backup copy of itself written in a simpler, flatter language. And if that's true, then the quantum foam we've been exploring isn't just foam. It's the universe's source code, flickering into existence one Planck-length pixel at a time. The implications are dizzying. If the holographic principle holds, then free will, consciousness, even time itself might be emergent phenomena, side effects of a deeper, simpler reality. It's a humbling thought. Everything you see, touch, and experience could be the cosmic equivalent of a shadow on a cave wall. Yet this isn't a call for nihilism. If anything, it's a testament to nature's ingenuity. The universe might be an illusion, but it's an illusion so detailed, so self-consistent, that it's indistinguishable from the real thing. And somewhere in the quantum foam's hidden language, the secret to decoding it all is waiting to be found. Quantum entanglement is the universe's ultimate magic trick. Two particles, separated by galaxies, somehow mirroring each other's every move faster than light could travel between them. Einstein famously called it spooky action at a distance. not because he doubted it, but because it defied everything classical physics held sacred. But what if the spookiness isn't just a bug in reality's code? What if it's a feature written into the very fabric of quantum foam? Picture this: every time particles become entangled, they're not really communicating across space. Instead, they're tapping into a deeper layer of reality, a hidden web of connections woven into spacetime itself. Think of quantum foam as the cosmic equivalent of a subway system. Two stations might be miles apart, but the tunnels beneath link them directly. Entangled particles could be like trains arriving at separate platforms simultaneously, not because they signaled each other, but because their paths were pre-wired into the network. This isn't just poetic speculation. Theories like quantum loop gravity and string theory suggest that spacetime might be built from interwoven threads or vibrating filaments, creating a natural lattice for entanglement to thrive. The implications are staggering. If entanglement rides the quantum foam's hidden highways, it could explain why this phenomenon isn't bound by speed or distance. Experiments have confirmed that entangled particles react in sync even when separated by thousands of kilometers, with no detectable signal passing between them. It's as if the universe has a built-in cheat code, bypassing the usual rules. Some researchers argue that this points to a non-local reality, one where separateness is an illusion and everything is fundamentally connected beneath the surface. Imagine stirring a pot of soup. The swirling broth appears chaotic, but every movement is linked by the liquid's underlying structure. Quantum foam might be the cosmic broth, and entanglement its silent choreography. But here's where it gets even wilder. If entanglement is rooted in spacetime's architecture, it could revolutionize how we understand gravity. Black holes, wormholes, even the Big Bang might share a common thread, literally. Some models propose that wormholes, those hypothetical shortcuts through spacetime, are just entanglement's macroscopic shadow. Two black holes could be entangled through quantum foam, their connection manifesting as a tunnel through folded space. It's a radical idea, but it's backed by math. Einstein's equations and quantum entanglement might be two sides of the same coin, the real test finding tangible evidence. Scientists are already using quantum foam's predictions to design experiments, like measuring whether entangled particles leave faint imprints in spacetime's geometry. Others are probing the vacuum for signs of entanglement entropy, a measure of how information spreads through the foam's hidden network. If these efforts succeed, we won't just solve a quantum mystery. We'll crack open a new window into reality itself, revealing a universe far more interconnected than we ever dreamed. So the next time you hear about spooky action, remember, it's not a glitch. It might be the universe whispering its deepest secret. That emptiness is alive, threaded with invisible ties binding everything together, and quantum foam. That's the loom weaving the tapestry. Time flows like a river, always forward, never backward. We remember yesterday but can't recall tomorrow, and dropped glasses shatter but never reassemble. This one-way street of existence, known as the arrow of time, is so baked into reality that we rarely question it. But quantum foam might be the hidden architect behind time's stubborn direction. Think of spacetime as a stretchy fabric. At large scales, it looks smooth and predictable, just like time seems to march steadily forward. But zoom into the quantum level, and that fabric becomes a turbulent foam, bubbling with particles that pop in and out of existence. Each of these fleeting fluctuations isn't perfectly symmetrical. Some leave faint imprints like footprints in wet sand. Over eons, these tiny asymmetries could add up, nudging the universe toward entropy and locking time into its irreversible flow. Here's where it gets even stranger. Quantum foam might not just influence time's direction, it could be recording it. every time a particle pair emerges from the vacuum, their brief existence leaves a subtle mark on spacetime's structure. Like grooves on a vinyl record, these imprints could store information about past events, creating a cosmic memory bank woven into the fabric of reality. This isn't just philosophy. The math suggests that black holes, those ultimate destroyers of information, might actually preserve data in their event horizons via quantum foam's intricate patterns. If true, then time's arrow isn't just a feature of our perception, it's etched into the universe's very bones. But could we ever rewind the tape? The laws of physics don't strictly forbid time reversal, yet it never happens on its own. Quantum foam might hold the key to this puzzle. Imagine a deck of cards scattered across a table. You could painstakingly sort them back into order, but it would take precise effort. Just like reversing time would require undoing every quantum fluctuation in perfect reverse sequence. The sheer scale of this task makes it practically impossible, like trying to unburn a forest one photon at a time. Yet some theories, like loop quantum cosmology, suggest that under extreme conditions, say, inside a black hole or at the birth of a new universe, time's arrow might temporarily wobble or even flip. The real test will come when we can probe spacetime at the Planck scale, where quantum foam's structure becomes visible. Future experiments with gravitational wave detectors or quantum computers might catch glimpses of these temporal fingerprints, revealing whether time's flow is written in foam like code. Until then, we're left with a breathtaking possibility that every second we experience, every memory we hold, is the echo of quantum chaos crystallizing into order. The universe doesn't just move forward, it remembers. Wormholes aren't just the stuff of sci-fi movies, they might be hiding in plain sight, woven into the very fabric of quantum foam. Picture spacetime as a turbulent ocean with waves constantly rising and falling. Most of these ripples vanish without a trace, but every so often, two distant points could briefly connect, forming a microscopic tunnel through the chaos. These aren't the giant, stable wormholes you'd fly a spaceship through. They're more like quantum fireflies, flashes of possibility that wink in and out of existence before you could even blink. The math suggests these fleeting passages could be nature's way of stitching the universe together at the smallest scales, a hidden network of shortcuts too tiny and unstable to notice. What's fascinating is how these wormholes might form. In the quantum foam's frenzy, pairs of virtual particles constantly emerge and annihilate. But under just the right conditions, their gravitational pull could twist spacetime into a temporary bridge, linking two points that would otherwise be light years apart. It's like stretching a rubber sheet until two distant spots touch, except here the sheet is reality itself, and the touch lasts less than a trillionth of a second. The catch, keeping one of these tunnels open long enough to be useful, would require something called exotic matter, a hypothetical substance with negative energy that could prop the wormhole's throat open against collapse. So far, we've never found proof such matter exists, but quantum foam doesn't need it. These tunnels aren't built to last. They're cosmic mayflies, born and gone in the same quantum breath. Yet, even if they're ephemeral, the implications are staggering. If we could somehow detect or stabilize a quantum wormhole, even for an instant, it might rewrite the rules of communication or travel. Imagine sending information through one of these tunnels, bypassing light speed entirely. A signal wouldn't need to cross the distance between 2 points. It would simply step through the cosmic backdoor. Some theories even suggest that entangled particles, those spooky partners that mirror each other across vast distances, might be linked by microscopic wormholes in the foam. It's a wild idea, but it could explain how they sync up without breaking relativity's speed limit. The real challenge proving any of this quantum wormholes would be impossibly small, far tinier than an atom, and vanish before any instrument could register them. But physicists aren't giving up. Experiments with ultra-sensitive detectors or quantum computers might one day catch indirect hints, like subtle distortions in spacetime's geometry or anomalous energy fluctuations. Others are simulating wormhole-like behavior in labs using holograms or superconducting materials, teasing out clues about how real ones might behave. So while we're not packing for a wormhole vacation anytime soon, their potential existence is a thrilling reminder. The universe is stranger than we imagine. Quantum foam doesn't just churn with particles, it might be threaded with hidden tunnels, a secret subway system linking every corner of reality, and if we ever learn to ride it, the cosmos would never feel so small again. Imagine the universe as a frozen lake on a winter morning, seemingly solid, stable, and serene. But beneath that icy surface, hidden currents swirl, and in rare moments, a single crack can spread with terrifying speed, shattering the entire sheet in seconds. That's the nightmare scenario of vacuum decay, a phenomenon so catastrophic it could rewrite reality itself. And it all starts in the quantum foam. Here's how it works. What we call a vacuum isn't truly empty. It's a seething false vacuum, a state of precarious balance where the laws of physics as we know them hold sway. But buried in the quantum foam's chaos, there's a chance, vanishingly small but real, that a tiny bubble of true vacuum could form. A place where the fundamental constants are different, where particles have new masses, where forces like electromagnetism or gravity might not even exist. If that bubble appears, it wouldn't just sit there. Like that crack in the ice, it would expand at the speed of light, obliterating everything in its path. Stars, planets, even spacetime itself would be rewritten in an instant with no warning, no escape. One moment, the cosmos as we know it, the next, an alien reality where nothing familiar survives. The terrifying beauty of this idea is that it's not pure speculation. The math checks out. Our universe's vacuum energy isn't at its absolute lowest possible state. It's metastable, like a ball balanced on a hill. Stable enough to last billions of years, but not forever. Quantum foam's fluctuations could, in theory, give that ball the nudge it needs to roll downhill, triggering a cascade that resets physics itself. The Higgs field, which gives particles their mass, might be the key player here. If its potential energy suddenly drops to a lower state, the ripple effect would be unstoppable. But before you panic, consider this. The odds of vacuum decay happening in any given year are astronomically low, less than 1 in a trillion. The universe has lasted 13.8 billion years without collapsing, which suggests our false vacuum is remarkably resilient. Still, the fact that it's even possible reveals something profound. The laws of physics aren't set in stone. They're more like a temporary arrangement, a cosmic ceasefire that could, under the right conditions, be overturned. What's truly humbling is that vacuum decay wouldn't just destroy us, it would erase any trace that we ever existed. No ruins, no echoes, no dying light. The universe wouldn't even notice, and yet, this existential fragility might also be the key to understanding deeper truths. If our vacuum isn't fundamental, then other vacuums, other universes with entirely different rules, could exist beyond our own. Some might be stillborn, collapsing instantly. Others could be sterile, devoid of the complexity needed for life. Ours, by sheer chance, struck the delicate balance that allowed galaxies, planets, and minds to emerge. So while vacuum decay is the ultimate cosmic sword of Damocles, it's also a reminder of how extraordinary our universe is. The quantum foam isn't just a curiosity, it's the canvas on which reality is painted, and the brush that could, at any moment, wipe it clean. The question isn't whether we'll ever see it happen, it's why it hasn't happened yet and what that tells us about the hidden architecture of everything. The idea that consciousness might reach down into the quantum foam and tweak reality sounds like something ripped from a psychedelic sci-fi novel. But believe it or not, this wild hypothesis has haunted the fringes of physics for decades. Picture a universe where the act of observation doesn't just measure particles but somehow molds them, where the mind isn't a passive spectator but an active participant in shaping the fabric of spacetime itself. It's a radical departure from the cold, deterministic laws of classical physics, and it all hinges on one of quantum mechanics' most infamous quirks, the observer effect. At its core, this theory suggests that the quantum foam's chaotic dance isn't entirely random, that consciousness, in some ill-defined way, nudges its fluctuations into order. Proponents point to experiments like the double-slit test, where particles behave differently when observed, as potential clues. In those moments, could the observer's awareness be imposing structure on the foam's turbulence? Some theorists, like physicist John von Neumann, even speculated that the collapse of a quantum wave function, the moment a particle's possibilities solidify into a single outcome, might require a conscious mind to trigger it. It's as if reality stays in a hazy superposition until someone looks, and the foam's froth crystallizes under the weight of attention. But before we rewrite the textbooks, let's be clear, mainstream science isn't buying it. The vast majority of physicists argue that observation in quantum mechanics just means interaction with any measuring device, not a human mind. A camera or a Geiger counter can collapse a wave function just as effectively as a brain. And the quantum foam's fluctuations, they're governed by pure math, not mysticism. Yet even skeptics admit the questions raised are tantalizing. If consciousness doesn't influence the foam, why does quantum mechanics seem to play by rules that feel almost tailor-made for paradox? Why does reality appear to choose an outcome only when probed? The truth is, we're still grappling with the hard problem of consciousness itself, how subjective experience emerges from neurons firing. Until we crack that, linking it to quantum foam is like trying to solve a riddle written in invisible ink. But the allure of this idea isn't just about proof, it's about possibility. It challenges us to consider whether the universe is more intertwined with perception than we ever dared imagine. Maybe the foam isn't just a backdrop, maybe it's a mirror reflecting back the profound mystery of what it means to be aware in a cosmos that seems at its core to thrive on uncertainty. Studying quantum foam is like trying to catch smoke with your bare hands. Every time you think you've got a grip, it slips away. The scales involved are almost incomprehensibly tiny. We're talking about lengths a billion trillion times smaller than an atom, and time frames so brief they make a nanosecond feel like an eternity. Direct observation. Forget about it, our best microscopes might as well be telescopes pointed at the wrong universe. So how do we even begin to study something that defies every tool we've got? The answer lies in the art of cosmic detective work, piecing together clues from the shadows this elusive phenomenon leaves behind. Take the Casimir Effect, for example. It's one of the few observable fingerprints of quantum foam's restless energy. By measuring the infinitesimal force between two metal plates in a vacuum, scientists can infer the presence of those flickering virtual particles. It's like deducing the shape of a hidden object by studying the ripples it makes in water. Then there's particle colliders, where smashing atoms at nearly light speed creates conditions so extreme that quantum foam's turbulence might briefly amplify. The debris from these collisions carries subtle hints, anomalies in energy distributions or unexpected particle behaviors that could trace back to spacetime's frothy underbelly. These aren't direct sightings, but they're the closest thing we've got to a cosmic breadcrumb trail. The real challenge isn't just the scale, it's the speed. Quantum foam's fluctuations happen faster than any instrument can snap a picture. Imagine trying to photograph a lightning strike with a camera that takes a week to click. By the time your shutter opens, the storm's long gone. That's why researchers are racing to build tools that operate on Planck time scales, the universe's smallest possible stopwatch ticks. Some are betting on quantum sensors so precise they can detect spacetime's graininess. Others are developing materials that might freeze foam-like fluctuations long enough to study them, like trapping a single frame of a hummingbird's wings mid-flap. The next frontier, high-energy accelerators like the proposed Future Circular Collider, which could reach energies high enough to probe the quantum foam's structure directly. Or space-based gravitational wave observatories, tuned to catch the faintest tremors in spacetime's fabric, tremors that might carry echoes of foam like turbulence. Even quantum computers could play a role, simulating foam-like conditions in controlled environments where we can tweak variables like cosmic lab rats. What's at stake isn't just academic curiosity. Cracking quantum foam's code could revolutionize everything from energy production to computing. Imagine harnessing vacuum energy or building materials that exploit spacetime's granularity for unbreakable encryption. But more than that, it's about rewriting our cosmic story. Every indirect measurement, every theoretical breakthrough brings us closer to answering the ultimate question: what is reality made of? Until then, we're left chasing shadows, but in those shadows, the universe whispers its deepest secrets. Quantum foam isn't just a playground for physicists, it's fuel for some of the most mind-bending stories ever told. Take Interstellar, where Matthew McConaughey's character plunges into a black hole and finds himself inside a tesseract, a higher dimensional space where time becomes a physical dimension. The film's depiction of gravity bending time and space isn't pure fantasy. It's rooted in real science, including the chaotic turbulence of quantum foam. The movie's scientific advisor, physicist Kip Thorne, worked to ensure the black hole's portrayal matched Einstein's equations, but the eerie, shifting dimensions Cooper navigates. That's the filmmakers tapping into the foam's reputation as a realm where reality itself frays at the edges. Books like Brian Greene's The Fabric of the Cosmos take it further, painting quantum foam as the hidden scaffolding of existence. Greene describes spacetime not as a smooth stage but as a quantum avalanche, where particles flicker in and out like static on an old TV. These ideas bleed into fiction too. In Contact, Carl Sagan's protagonist travels through a wormhole network, a concept that wouldn't exist without the foam's theoretical underpinnings. Even Doctor Who plays with the idea, dressing up its time travel mechanics with technobabble about timey-wimey quantum fluctuations. The common thread: these stories treat the foam as a frontier, a place where the rules break down and anything becomes possible. But pop culture's love affair with quantum foam isn't just about spectacle. It mirrors humanity's oldest questions. Are there hidden dimensions? Can we bend time? Is reality just a projection? Philosophers have latched onto these themes, arguing that if space-time is fundamentally grainy, then our perception of a smooth, continuous world might be an illusion. Some even suggest consciousness could interact with the foam's fluctuations, an idea that veers into metaphysics but fascinates audiences nonetheless. The Matrix trilogy, with its simulated reality, owes a debt to this thinking, imagining a universe where the code of existence is as malleable as quantum foam's froth. Of course, Hollywood takes liberties. You won't find astronauts surfing quantum vortices in real life, at least not yet, but these exaggerations serve a purpose. They make the cosmos feel alive, unpredictable, and wondrous, reminding us that science's wildest theories can be as thrilling as any myth. The next time you watch a character step through a portal or tweak the fabric of reality, remember, the inspiration isn't just a writer's whim. It's the universe's own blueprint whispering through the static of the quantum void. Mathematics isn't just a tool for studying quantum foam, it's the only language this chaotic realm seems to understand. Think of it like trying to predict the path of a tornado using nothing but the scribbles of wind on paper. Physicists wield equations like cosmic decoders, translating the foam's frenzied whispers into something we can almost grasp. Take topology, the branch of math that studies shapes and their properties under deformation. To model quantum foam, scientists use twisted, multi-dimensional geometries that would make a pretzel look simple. These aren't just abstract doodles, they're blueprints for how spacetime might fold, knot, or even tear at scales a billion times smaller than an atom. Then there's quantum field theory, where numbers dance in ways that defy intuition. The equations here don't just describe particles, they track the ebb and flow of energy itself, capturing how virtual particles borrow from the vacuum and repay their debt in fleeting instants. It's like balancing a checkbook where the numbers blink in and out of existence, but the math has limits. Current theories hit a wall at the Planck scale, where gravity's pull becomes as wild as the foam itself. The equations that flawlessly predict electron orbits or galaxy rotations suddenly spit out infinity's nonsense answers, screaming that we're missing something profound. This isn't just about cleaning up messy calculations. The gaps in our math might be hiding revolutionary physics. Some researchers believe the key lies in unproven theories like non-commutative geometry, where space-time coordinates refuse to follow neat arithmetic rules. Imagine multiplying two numbers and getting a different result depending on the order, a mathematical twilight zone where the foam's chaos finds order. Others pin their hopes on twistor theory, a framework that replaces points in space with swirling, hyperdimensional ribbons. It's as if the universe's source code was written in a dialect we're only now learning to pronounce. The boldest ideas come from merging math with sheer imagination. Conformal field theory, for instance, suggests that quantum foam's turbulence might follow patterns similar to those in exotic materials like graphene. String theory's equations hint at hidden symmetries, secret harmonies in the foam's noise that could unify gravity with quantum mechanics. Even artificial intelligence is joining the hunt, scouring millennia of mathematical archives for forgotten gems that might crack the foam's cipher. What's thrilling isn't just the potential answers, it's the sheer creativity of the quest. Every scribbled equation, every midnight epiphany at a chalkboard, is a flare shot into the darkness, probing for shapes we can't yet see. The right formula won't just solve a puzzle, it could redefine emptiness itself, revealing that what we call nothing is the most vibrant something of all. And when that breakthrough comes, it won't be in a flash of lab equipment or a telescope's lens. It'll be written in numbers, the universe's native tongue, waiting for someone bold enough to listen. Quantum foam doesn't just challenge physics, it upends philosophy. If the void between stars and atoms is a seething hive of activity, then what does it mean for something to truly exist? Ancient philosophers like Parmenides argued that nothingness was impossible, a void couldn't be by definition. But quantum foam takes this idea and twists it into a paradox. The vacuum isn't empty, yet it isn't filled with anything permanent either. It's a realm where particles flirt with existence, borrowing reality for fractions of a second before vanishing like ghosts. This isn't just a scientific curiosity. It forces us to ask, is the universe fundamentally made of stuff, or is stuff just a fleeting pattern in a deeper, more chaotic substrate? Materialists might point to the foam's physicality. Those virtual particles leave measurable effects, like the Casimir force nudging metal plates together. To them, reality is built from tangible, if ephemeral, building blocks, but idealists see something else entirely. If observation plays a role in collapsing quantum probabilities, could the foam's chaos only crystallize into real particles when consciousness interacts with it? It's a modern spin on Bishop Berkeley's old question: if a tree falls in a quantum forest with no one to observe it, does it make a sound or even exist at all? The foam's evanescent nature makes both perspectives eerily plausible. Then there's the question of boundaries. We're used to thinking of objects as distinct, a rock here, a star there. But quantum foam suggests that at the smallest scales, separateness might be an illusion. Particles emerge from the same seething background, entangled and interconnected. Eastern philosophies like Buddhism have long argued that reality is a web of interdependence with no true divisions. Quantum foam, in its own bizarre way, echoes this. The universe might be less like a collection of billiard balls and more like a turbulent ocean, where what we call things are just temporary crests in an endless wave. But the most unsettling implication is humility. Human intuition evolved to navigate a world of medium-sized objects moving at medium speeds. Quantum foam operates on scales and times so alien that our brains literally can't picture them. It's like trying to describe color to someone born blind. This doesn't mean reality is unknowable, just that it's far stranger than our senses ever hinted. The foam whispers that existence is richer, weirder, and more mysterious than our language or logic can fully capture. And that, perhaps, is the most profound lesson of all. The universe owes us no obligation to make sense. The idea of tapping into quantum foam for technology sounds like something ripped from the pages of a futuristic novel, but the physics behind it is startlingly real. Imagine a world where the empty space around us isn't just void but an untapped reservoir of energy, where the very fabric of spacetime could be harnessed to power civilizations or bend the laws of motion. This isn't just fantasy. The quantum foam's ceaseless churn of virtual particles hints at a staggering possibility: vacuum energy. Scientists call it zero-point energy, the baseline hum of the universe that persists even at absolute zero. If we could extract even a fraction of it, the implications would rewrite human history. A single cubic centimeter of empty space, according to quantum theory, contains enough energy to boil all the oceans on Earth. The challenge: figuring out how to siphon it without tearing spacetime apart in the process. One of the most tantalizing prospects is zero-point energy reactors. Unlike conventional power sources that rely on burning fuel or splitting atoms, these hypothetical devices would draw directly from the quantum foam's fluctuations. The Casimir Effect already shows us that vacuum energy can exert real, measurable force, so why not channel it? Experiments with microscopic plates and advanced nanomaterials are inching toward proof of concept, though the engineering hurdles remain colossal. The real breakthrough would come if we could stabilize and amplify these quantum jitters, transforming them into a clean, limitless power supply. Picture spacecraft fueled not by bulky propellants but by the void itself, or cities lit by generators humming with the latent energy of empty space. The obstacles are immense, but the potential is cosmic. Then there's the holy grail of interstellar travel: warp drives. Einstein's equations allow for the bending of space-time, and quantum foam might hold the key to doing it on demand. Theoretical designs like the Alcubierre warp drive rely on manipulating spacetime's geometry, creating a bubble where the fabric of reality contracts in front of a ship and expands behind it, effectively surfing the cosmos without breaking light speed limits. The catch, it requires exotic matter with negative energy, something we've never observed. But here's where quantum foam enters the picture. If vacuum fluctuations can generate fleeting particles with unusual properties, could we learn to isolate or replicate them? Some physicists speculate that advanced civilizations might already be using such technology, bending the foam's chaos into controlled corridors between stars. Quantum computing, too, could leap forward by embracing the foam's unpredictability. Today's quantum qubits are notoriously fragile, easily disrupted by the slightest noise. But what if we could engineer qubits that sync with vacuum fluctuations instead of fighting them? Instead of treating quantum foam as interference, future systems might treat it as a resource, leveraging its natural turbulence to perform calculations impossible on classical machines. Researchers are already exploring vacuum states in quantum circuits, where the foam's behavior could be harnessed for ultra-secure encryption or simulating complex molecular interactions. It's like trying to ride a wild stallion instead of taming it, a shift from suppression to collaboration. Of course, these ideas dance on the edge of science fiction. The quantum foam's energy is elusive, its behavior maddeningly erratic. Stabilizing it for practical use would require breakthroughs we can barely envision today. Yet history shows that today's impossibilities often become tomorrow's tools. The transistor, the laser, even nuclear fission, all were once dismissed as impractical theories before revolutionizing the world. The difference now is scale. We're not just tweaking materials or particles, we're grappling with the substrate of reality itself. What makes this pursuit so electrifying isn't just the technology, it's the philosophy. Harnessing quantum foam would mean humanity moving from passive observers of the universe to active participants in its deepest mechanics. We wouldn't just live in space-time, we'd shape it. And while the path forward is fogged with unknowns, one thing is clear: the quantum foam isn't just a curiosity. It's a challenge, a cosmic gauntlet thrown down, daring us to rethink what's possible. The day we unlock even a fraction of its secrets, the word impossible might vanish from our vocabulary altogether. Not every physicist is convinced that quantum foam is the final answer. For some, it's more like a rough sketch, a placeholder for deeper physics we haven't uncovered yet. Think of it like an ancient map with dragons at the edges, marking uncharted territory. The foam's chaotic nature might not be fundamental, but instead a sign of something more structured lurking beneath. One compelling alternative comes from emergent gravity theories, which suggest that gravity isn't a force woven into space-time but a side effect of deeper, hidden processes like how temperature emerges from the jostling of atoms. In this view, quantum foam's turbulence could be a surface ripple, not the ocean itself. Then there's pilot wave theory, a radical reimagining of quantum mechanics that ditches randomness entirely. Instead of particles popping in and out of existence, this framework proposes that every particle is guided by an invisible pilot wave, riding its contours like a surfer on a hidden tide. In this model, the vacuum's apparent frothiness might not be spontaneous creation, but the result of unseen waves shaping reality from behind the scenes. It's a controversial idea, but it challenges the foam's dominance by offering a deterministic alternative to quantum chaos. The debate isn't just academic nitpicking, it cuts to the heart of how we understand reality. If quantum foam is real, then spacetime is fundamentally wild and unpredictable. If alternatives like emergent gravity hold water, then what looks like chaos might be the shadow of order we can't yet see. This tension is exactly what makes physics so thrilling. Every unanswered question is an open door, and every competing theory is a lantern lighting a different path forward. What's fascinating is how these disagreements reveal science in action. Quantum foam isn't dogma, it's a hypothesis being stress-tested from every angle. Some researchers are probing the foam's limits with ultra-precise gravity experiments, while others are simulating exotic models where space-time condenses from more basic building blocks like droplets forming from vapor. Even if foam turns out to be just one piece of a larger puzzle, the hunt for answers is reshaping our cosmic worldview. After all, the best mysteries aren't the ones we solve, they're the ones that keep us questioning. If quantum foam can birth particles from nothingness, why not entire universes? Picture a cosmic ocean where bubbles of spacetime continuously form, each one inflating into its own separate reality with its own unique rules. Our universe, in this view, isn't special, it's just one bubble among countless others, each floating in an infinite multiverse stew. Some of these bubbles might collapse instantly, snuffed out before they can grow beyond a speck. Others could stretch into vast cosmos where gravity is repulsive, light moves backward, or atoms never form. The unsettling implication: our universe's life-friendly constants, the precise strength of gravity, the exact mass of an electron aren't inevitable. They're a random roll of the dice, a lucky accident in a sea of failed experiments. This foamy multiverse idea didn't emerge from wild speculation. It's a natural extension of inflation theory, which suggests our universe underwent exponential expansion in its first moments. If spacetime can balloon once, why not endlessly? Quantum foam's turbulence provides the perfect breeding ground. Tiny fluctuations in the vacuum could nucleate new bubbles, each pinching off into its own isolated reality. String theory adds fuel to the fire, with its landscape of possible universes numbering in the tens of thousands. In this framework, what we call the universe might just be one page in an infinite library, each volume written in a different physical dialect. Critics argue this is untestable metaphysics, not science. Without any way to peer beyond our cosmic horizon, how could we ever confirm other bubbles exist? Yet supporters counter with eerie clues. The cosmic microwave background, the afterglow of the Big Bang, bears faint anomalies that some interpret as bruises from collisions with neighboring universes. Others point to dark energy's mysterious uniformity, asking if it's the signature of a larger multiverse structure gently shaping our bubble from outside. These aren't smoking guns, but they're tantalizing breadcrumbs. The philosophical stakes are dizzying. If the multiverse is real, humanity's place in the cosmos shrinks from special to statistically inevitable. In an infinite foam of universes, every possible outcome must happen somewhere. Countless versions of you reading this, countless where you never existed. Some find this liberating, others existentially jarring. But whether the foamy multiverse is fact or fiction, its real power lies in stretching our imagination. It forces us to confront how little we know, and how much wonder might still be hiding in the quantum depths, waiting to rewrite reality's rules all over again. Light speed isn't just a cosmic speed limit. It's a mystery woven into the fabric of spacetime itself. For over a century, we've known that nothing outpaces light's 299,792,458 meters per second in a vacuum. But why that number? Why not faster or slower? The answer might lie in quantum foam's turbulent depths, where spacetime's microstructure could be acting like invisible speed bumps for photons. Imagine light as a surfer gliding across the ocean. On calm days, it races unimpeded, but toss in a churning foam of waves, and suddenly every forward motion meets resistance. At scales a billion times smaller than an atom, spacetime's froth could be doing the same to light, subtly scattering high-energy photons. forcing them to take slightly longer paths through the chaos. Over cosmic distances, those tiny detours add up, giving us the universal speed limit we observe. This idea isn't just poetic speculation. Certain quantum gravity models predict that photons with ultra-high energies far beyond what our particle colliders can produce should interact with spacetime's graininess. Like a marble rolling through a field of pebbles, their trajectory would deviate ever so slightly, a phenomenon called vacuum dispersion, the twist. We might already have evidence. When astronomers observe gamma-ray bursts from the edges of the universe, the highest energy photons sometimes arrive a fraction of a second later than their lower energy counterparts. It's as if the fabric of space itself is sifting light by wavelength, a fingerprint of quantum foam's hidden architecture. But here's where it gets even stranger. If foam-like structures really do slow light, they might also explain why nothing can exceed its speed. In Einstein's relativity, light's velocity isn't just a barrier, it's a fundamental property woven into causality. Exceed it, and time itself could reverse, breaking the chain of cause and effect. Quantum foam might be nature's way of enforcing this rule. A cosmic traffic cop ensuring no particle ever outruns reality's underlying framework. Some theories even suggest that at Planck scales, spacetime's froth becomes so dense that it acts like a superfluid, with light speed emerging as a sort of viscosity in the vacuum. The implications ripple far beyond physics textbooks. If light speed is tied to quantum foam, then altering the foam's structure, say, with unimaginable energies, could theoretically tweak the speed limit itself. Wormholes, warp drives, and other sci-fi staples hinge on bending spacetime's rules, but foam's resistance might be the ultimate obstacle. Even more tantalizing is the possibility that light speed wasn't always constant. In the early universe, when quantum foam's turbulence was fiercer, light might have moved slower, leaving faint imprints in the cosmic microwave background. Future telescopes could hunt for these echoes, revealing whether our most fundamental constant is truly unchanging, or just an average in a frothy, fluctuating sea. What's breathtaking is how this connects the unimaginably small to the cosmic. The same quantum jitters that shape virtual particles might also dictate how light crosses the universe, threading microscopic chaos into the grand tapestry of physical law. And if we're right, then every beam of sunlight, every twinkle from a distant star, carries not just energy, but the encrypted signature of spacetime's hidden heart. Gravitational waves are like cosmic sonar ripples in spacetime that echo from the most violent collisions in the universe. When two black holes spiral into each other, they don't just vanish silently. They send shockwaves through the fabric of reality itself, stretching and squeezing space as they travel outward at light speed. But here's the twist: these waves don't glide through a perfectly smooth universe. They pass through the quantum foam's turbulent sea, where spacetime is anything but serene. Think of it like a stone dropped into a choppy ocean. The ripples don't just spread cleanly, they jitter and scatter, distorted by the waves beneath them. That's exactly what some physicists believe happens to gravitational waves on the smallest scales. Quantum foam's granularity, its pixel-like structure, could leave faint fingerprints on these ripples, subtly altering their shape or frequency as they travel. It's as if spacetime itself has texture, and gravitational waves are the sensitive fingers feeling its grooves. The effect would be vanishingly small, but not undetectable. Future observatories like LISA, the Laser Interferometer Space Antenna, could be precise enough to spot these anomalies. Imagine listening to a symphony with headphones so advanced you can hear the musician's fingers sliding on the strings. That's the level of detail we're chasing. The stakes couldn't be higher. If gravitational waves bear the scars of quantum foam, it would be the first direct evidence of spacetime's granular nature. Current models suggest these distortions might manifest as a kind of noise in the wave signal, tiny hiccups that don't fit the clean predictions of Einstein's general relativity. Some theories even propose that foam's turbulence could cause gravitational waves to disperse slightly, with high-frequency ripples arriving a fraction of a second earlier or later than their lower-frequency counterparts. It's a cosmic version of light splitting into a rainbow, but for gravity itself. But why stop at black holes, neutron star mergers, supernova? Even the primordial echoes of the Big Bang could carry these quantum whispers. Each cataclysm sends waves through spacetime's foam, and each could reveal a different facet of its structure. The early universe, in particular, might hold the most dramatic clues. In the first moments after the Big Bang, quantum foam's turbulence was unimaginably fierce, like an ocean in a hurricane. Gravitational waves from that era, if we can ever detect them, might bear the unmistakable scars of that chaos, frozen in time like fossils in cosmic amber. Yet the real magic lies in what this could unlock. If we can decode how gravitational waves interact with quantum foam, we might finally bridge the gap between relativity and quantum mechanics, the holy grail of modern physics. It's like discovering that two languages we thought were unrelated actually share a hidden alphabet. Every ripple, every distortion could be a letter in spacetime's deepest dialect waiting to be read. And with each new detection, we're not just listening to the universe's loudest crashes, we're tuning into its quietest, most profound whispers. Black holes aren't just cosmic vacuum cleaners, they're information shredders, or at least that's what classical physics would have us believe. Toss a book into a black hole, and according to Einstein's general relativity, it's gone forever, crushed into the singularity's infinite density. But here's the problem. Quantum mechanics insists that information can never truly disappear. Every particle, every interaction leaves some trace, some fingerprint in the universe's ledger. This clash isn't just academic nitpicking, it's a crisis at the heart of physics, a paradox so deep that even Stephen Hawking famously bet against his own theory before conceding he might be wrong. So where does the information go? The answer might be hiding in the quantum foam's chaotic dance. Imagine the event horizon of a black hole as a stormy sea, with waves of quantum foam churning at its edge. When virtual particle pairs pop into existence here, one particle falls inward while the other escapes as Hawking radiation. At first glance, this seems like a one-way trip for information. The infalling particle carries it into oblivion. But the foam's turbulence could be playing a far subtler game. Some theories suggest that the information isn't destroyed at all. Instead, it's imprinted onto the event horizon's surface like a cosmic hologram. Every particle swallowed by the black hole leaves a faint pixel on this boundary, a scrambled but preserved record of what fell in. Over time, as Hawking radiation leaks away, those pixels could be slowly decoded, like a message written in vanishing ink. This isn't just poetic speculation. The math behind holographic principles shows that the surface area of a black hole's event horizon can encode an amount of information proportional to its size, not its volume, a clue that the universe might be running a cosmic backup system. Quantum foam's fluctuations could be the mechanism, with each virtual particle interaction subtly altering the horizon's microstructure. It's as if the black hole's surface is a frenetic hard drive, constantly rewriting itself to keep track of the chaos within. And when the black hole finally evaporates, that information isn't lost, it's radiated back into the universe, piece by piece, in the Hawking particle's quantum states. But there's a catch. If information escapes via Hawking radiation, It's not in any form we'd recognize. Imagine burning a library full of books and claiming the information still exists because the smoke carries the ashes. Technically true, but reassembling Shakespeare from the soot would be impossible. That's the challenge with black holes. The information might be preserved, but it's scrambled beyond any practical recovery. Quantum foam's role here is critical. Its chaotic nature could be the scrambler, mixing and encrypting the data so thoroughly that only the universe itself holds the decryption key. The stakes are higher than just black holes. If information is truly preserved, even in these extreme conditions, it hints at a universe with unbreakable rules, a cosmos where nothing, not even the most violent phenomena, can erase its own history. This would be a triumph for quantum mechanics, but it also raises eerie questions. If every particle's path, every event, is forever recorded in some form, does that mean the universe has a built-in memory? Are we living in a cosmic simulation where every variable is meticulously logged? Or is it simply a fundamental truth that existence itself is a web of connections where nothing is ever truly isolated or lost? The answer might lie in the foam's fine print. Future gravitational wave detectors or quantum computers could hunt for the faint echoes of information in Hawking radiation, searching for patterns in the noise. Some theorists even propose that black holes aren't the end of information but transformers, repackaging it into new forms we've yet to understand. One thing's for certain, solving this paradox won't just tell us what happens to a particle falling into a black hole. It'll reveal how the universe keeps its books balanced even in the face of oblivion, and quantum foam, with its restless energy and hidden patterns, might be the accountant. Simulated reality theories turn the quantum foam from a scientific curiosity into something far more provocative. What if it's not just the fabric of space-time, but the literal code of the universe? Think of the most realistic video game you've ever played. No matter how detailed the graphics, zoom in far enough, and you'll eventually see the pixels, the jagged edges where the simulation's resolution hits its limit. Quantum foam, with its frenetic particle-antiparticle pairs and Planck-scale turbulence, could be nature's version of those pixels. Every flicker, every fluctuation might not be random chaos, but the universe's processor churning through calculations to maintain the illusion of a seamless reality. This isn't just sci-fi musing. The idea that our cosmos could be a simulation has gained traction among philosophers and physicists alike. Silicon Valley visionaries like Elon Musk have famously argued the odds are high we're living in a digital construct, while academics like Nick Bostrom have formalized the simulation hypothesis with probability theory. But where does quantum foam fit in? If reality is a computation, then the foam's fluctuations could be the unavoidable noise of the system artifacts of finite processing power. Picture a supercomputer running a hyper-advanced universe simulator. Even with boundless resources, it would still need to approximate certain details at the smallest scales, rounding off numbers or skipping steps to save cycles. Those shortcuts might manifest as the foam's unpredictable jitter, the cosmic equivalent of a laggy frame rate or glitchy textures. Critics dismiss this as untestable metaphysics, but there are intriguing hints. Take the Planck length, the smallest possible unit of space, beyond which measurements lose meaning. It's eerily similar to a pixel's minimum size in a digital display. Then there's quantum indeterminacy, where particles lack definite properties until observed. In a simulation, this could be lazy loading data only rendered when needed to conserve memory. Even the holographic principle, which suggests the universe's information might be encoded on a two-dimensional boundary, aligns with how modern graphics engines optimize 3D worlds by projecting them from simplified surfaces. Yet the debate isn't just about physics, it's about the nature of existence itself. If the foam is code, who or what wrote it? Some theorists propose advanced civilizations running ancestor simulations, while others imagine a self-generating mathematical universe where reality emerges from pure logic. The unsettling corollary: if we're in a simulation, glitches or cheat codes might exist, anomalies where the rules bend. Quantum foam's extreme behaviors, like particles tunneling through barriers or entangled pairs sinking instantly across light years, could be the cracks where the simulation's underlying architecture peeks through. But here's the twist: even if the foam isn't proof of a simulated reality, treating it as such has practical value. Scientists already use quantum computers to simulate molecular interactions too complex for classical machines. By reverse engineering spacetime's code, we might uncover shortcuts to warp drives, zero-point energy, or even consciousness itself. The foam's chaos could be a puzzle waiting to be hacked, a cosmic API hidden in plain sight. Whether metaphor or literal truth, the simulation hypothesis forces us to confront a humbling possibility. The universe might not just be stranger than we imagine, but stranger than we can imagine. And quantum foam, with its cryptic fluctuations, could be the first clue that reality is deeper, weirder, and more malleable than we ever dared dream. The power to manipulate quantum foam isn't just a scientific breakthrough, it's a Pandora's box of ethical dilemmas. Imagine holding a cosmic dial that could tweak the very fabric of spacetime. On one hand, we might unlock limitless energy, warp speed travel, or even the ability to stitch together wormholes. But turn that dial too far, and we risk unraveling reality itself. The vacuum isn't just empty space, it's a delicate equilibrium, a house of cards held together by quantum rules we barely understand. Tug at one thread, and the whole structure could collapse. Take vacuum decay, for example. If our experiments accidentally create a bubble of true vacuum with lower energy, that bubble could expand at light speed, rewriting the laws of physics in its wake. One misstep, and the universe as we know it could vanish, not with a bang, but with a silent, irreversible flicker. Then there's the butterfly effect on a cosmic scale. Quantum foam's turbulence underpins everything from atomic stability to the flow of time. Mess with its structure, and we might inadvertently alter the binding forces that hold atoms together. Picture a world where the strength of electromagnetism fluctuates unpredictably. Chemistry itself would become chaotic, turning water into explosive gas or rendering DNA unstable. Even seemingly benign technologies like Casimir Effect generators harvesting vacuum energy could have cascading consequences. Drain too much energy from the quantum foam, and spacetime might develop bare patches, regions where particles can't form properly. It's like stripping insulation from a wire, except the wire is the fabric of existence. The ethical parallels to nuclear physics are impossible to ignore. When scientists first split the atom, few foresaw the dual-edged sword of energy and annihilation it would unleash. Quantum foam manipulation could be orders of magnitude more volatile. Wormholes, for instance, might offer interstellar shortcuts, but they could also become catastrophic time machines. A single unstable wormhole might loop causality into paradoxes, erasing events from history or spawning infinite copies of reality. And who gets to control such technology? The potential for weaponization, collapsing enemy states into false vacuums, or weaponizing artificial black holes makes nuclear warheads look quaint by comparison. Yet the greatest risk might be philosophical. If we master quantum foam, we're no longer just inhabitants of the universe, we become its architects. That godlike power comes with existential vertigo. Do we have the wisdom to reshape spacetime when we can't even agree on how to share Earth's resources? History shows that humanity often races ahead with discovery, only to grapple with ethics later. But with quantum foam, there may be no later. A single irreversible mistake could erase the very framework for morality itself. This isn't a call to abandon research, it's a plea for humility. The same quantum foam that baffles us might also guard its secrets with built-in fail-safes. Perhaps the Planck scale isn't just a barrier of smallness, but a cosmic do-not-cross tape. Or maybe the universe is more resilient than we fear, its foam-like structure flexing to absorb our experiments without breaking. Either way, one truth remains: the deeper we probe into reality's foundations, the more we're confronted not just with equations but with choices. And those choices about how, when, or if to meddle with spacetime's quantum undercurrents will define not just our future, but the future of reality itself. Quantum foam might sound like something you could scoop into a jar, a mysterious cosmic ether waiting to be harnessed. But here's the reality. It's not a substance, not a fluid, not anything you could ever hold in your hand. Those sci-fi visions of harnessing the quantum foam to power warp drives or psychic abilities, pure fantasy. The truth is far stranger and far more fascinating. Quantum foam is a behavior of spacetime itself, a frenzy of fluctuations so small and fleeting that they defy every intuition we've built from our macroscopic world. It's like trying to catch the wind by grabbing at individual air molecules. The harder you try to pin it down, the more it slips through your fingers. One of the biggest misconceptions is that quantum foam explains the paranormal telekinesis, ESP, or other psychic phenomena. Sure, the foam's chaos seems mysterious, but there's zero scientific evidence linking it to human consciousness or supernatural events. In fact, the opposite is true. Quantum effects like entanglement or superposition are notoriously fragile, collapsing the moment they interact with their environment. Your thoughts aren't bending space-time, they're the product of biochemistry firing in the warm, wet, decidedly classical environment of your brain. The foam's randomness isn't a doorway to the unknown, it's a mathematical feature of the vacuum, governed by equations, not wishes. Then there's the free energy myth. YouTube is full of wild claims about extracting limitless power from quantum foam's fluctuations, often citing the Casimir Effect as proof. Here's the catch: while the Casimir Effect does demonstrate vacuum energy's reality, it's not a magic battery. The energy you could theoretically extract from these fluctuations is negligible, like trying to power a city by collecting static electricity from carpet shocks. Worse, the laws of thermodynamics still apply. Even if you could tap into quantum foam's energy, you'd spend more energy containing and stabilizing it than you'd ever gain. It's the universe's ultimate tease, a treasure chest locked inside a black hole. Pop science often paints quantum foam as the answer to everything from gravity control to time travel, glossing over the messy details. Yes, it's a cornerstone of cutting-edge physics, but it's not a cosmic cheat code. The foam's behavior is constrained by rigorous math and experimental limits. Wormholes might be mathematically possible, but stabilizing them would require exotic matter we've never observed. Warp drives. Even if Alcubierre's equations hold, the energy requirements are astronomical. These ideas aren't impossible, but they're light years away from practical application. The real magic of quantum foam isn't in bending the rules, it's in revealing how little we truly understand about the rules themselves. So what do we know for sure? Quantum foam is the universe's way of reminding us that empty space is a myth. It's a dynamic, seething arena where particles wink in and out of existence, where gravity and quantum mechanics collide in ways we're still decoding. But it's not a tool, not a weapon, not a gateway to other dimensions, at least not in any way we've learned to wield. The line between fact and fiction here isn't just thin, it's fractal, twisting back on itself with every new discovery. And that's the real wonder, not the myths we spin, but the truths we're still unraveling, one plank-length puzzle at a time. The quest to crack quantum foam's secrets is accelerating, with experiments now pushing beyond theory into uncharted territory. CERN High Luminosity LHC upgrade, set to smash particles at unprecedented energies by 2029, could finally reveal spacetime's granular structure. Imagine hurling protons together so violently that the collision's shockwaves ripple through the quantum foam itself, momentarily amplifying its fluctuations like seismic waves exposing buried fault lines. These collisions might spawn exotic particles or fleeting spacetime defects, tiny cracks in reality's facade that could betray the foam's hidden architecture. Even more tantalizing are plans for the future circular collider, a 57-mile ring that would dwarf the LHC, probing energies where gravity and quantum mechanics might visibly intertwine. But brute force isn't the only tool in play. Across the globe, quantum gravity probes are taking subtler approaches. The Fermilab holometer, for instance, fires lasers down perpendicular tunnels, measuring whether spacetime's fabric wobbles at Planck-scale frequencies. It's like tuning a radio to static, hoping to catch the universe's background hum. Meanwhile, tabletop experiments with supercooled diamonds or levitated nanoparticles aim to detect quantum foam's faint tremors, technologies so precise they could sense a virus's heartbeat. These aren't just incremental steps, they're potential paradigm shifts, leveraging quantum control to spy on spacetime's innermost workings. Theoretical frontiers are equally dizzying. Some physicists are ditching smooth spacetime entirely, modeling the universe as a cosmic network of interconnected nodes, a framework called quantum gravity. Picture reality as a vast dynamic mesh where distance emerges from how many links separate points, not some pre-existing grid. Other models, like causal sets, treat spacetime as a cascade of discrete events, with quantum foam being the froth atop this deeper, more orderly structure. These aren't abstract daydreams, they're testable hypotheses. If spacetime is indeed pixelated, high-energy cosmic rays could arrive slightly scrambled, their paths nudged by the foam's granularity like light bending through frosted glass. The stakes couldn't be higher. Success might unveil the universe's operating system, revealing how gravity emerges from quantum chaos. Failure could mean confronting an even stranger truth, that quantum foam isn't just hard to study, but fundamentally unknowable, its secrets forever veiled by the limits of measurement. Either way, the next decade promises to rewrite textbooks, whether through lab breakthroughs or cosmic observations. We're not just exploring the foam. We're learning how to listen to its whispers, and they might just change everything. Quantum foam isn't just a scientific concept, it's a mirror held up to the very nature of reality, reflecting back questions that have haunted thinkers for millennia. Every flickering particle, every warped thread of spacetime whispers the same profound truth. The universe is far stranger, far more alive than our senses can perceive. Consider the humble atom, once thought to be the smallest indivisible unit of matter. Then we split it, revealing protons, neutrons, quarks, and now this foamy sea beneath even those. Each layer we peel back doesn't simplify reality. It reveals new complexities, new mysteries waiting in the depths. What makes quantum foam so extraordinary isn't just its behavior, it's what that behavior implies about existence itself. The vacuum isn't empty, time isn't absolute, space isn't smooth. These aren't minor tweaks to our worldview. They're seismic shifts that rattle the foundations of how we understand everything from the tiniest particles to the grandest cosmic structures. When researchers at CERN smash particles together, or when astronomers study the afterglow of the Big Bang, they're not just collecting data, they're reading the universe's deepest diary, page by quantum-foamed page. The philosophical implications are staggering. If reality is this fluid at its core, what does that say about the nature of permanence, about cause and effect? About the very fabric of being, ancient philosophers debated whether the universe was made of water, fire, or atoms. Today, we grapple with a far more radical proposition that it might not be made of stuff at all, but of dynamic relationships, of probabilities and potentials dancing in the void. The foam challenges us to reconsider not just how the universe works, but what it fundamentally is. And the most exhilarating part, this isn't the end of the story, it's the opening chapter. Every unanswered question about quantum foam is an invitation, a cosmic puzzle box waiting to be solved. Will we find wormholes lurking in the turbulence, unlock the secrets of dark energy, discover that space-time itself is pixelated? The tools to find out are being built right now, in particle colliders stretching for miles, in quantum computers processing impossible calculations, in telescopes peering back to the universe's first moments. What awaits us in the quantum depths may defy all expectations. Perhaps the foam will reveal hidden dimensions, or prove to be the key to uniting gravity with quantum mechanics. Maybe it will show us that our universe is just one bubble in an infinite multiverse, each with its own laws written in foam. One thing is certain, the journey into this subatomic frontier will change us. Not just our technology or our science, but our very understanding of what it means to exist in this shimmering, uncertain, astonishing cosmos. The quantum foam isn't just part of the universe. In a very real sense, it is the universe, and we're only beginning to learn its language.